NASA's Jet Propulsion Laboratory presents the Von Kármán Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, ladies and gentlemen. How are we all tonight? Good, that's what I like to hear. Well, thanks for coming out again to join us for this edition of the Theodore Von Kármán Lecture Series. Tonight, let's start that again, shall we? Titan, Saturn's largest moon and the only moon in the solar system enshrouded in a thick atmosphere, has fascinated observers since its discovery in 1655. When the Cassini-Huygens mission to Saturn, a joint NASA-ESA-ASI mission, reached Saturn in July of 2004, the Huygens probe was released from the orbiter on Christmas Day and reached Titan on January 14, 2005. Upon arrival, it drifted down to the surface, returning data and spectacular images to a worldwide audience. Since then, the Cassini orbiter has gone on to complete almost 80 close flybys of Titan and has revealed the surface, which is normally hidden by a thick hydrocarbon atmosphere, to be a complex, exciting, and remarkably Earth-like place. There are miles and miles of dunes, lakes of methane and ethane, and exotic features that might possibly be ice volcanoes. Humanity has been fascinated by the solar system's second largest moon for hundreds of years, and now we're sitting ringside as Titan begins to reveal its mysteries. Tonight's guest started her career at NASA's Jet Propulsion Laboratory with a bang. Her first and still favorite experience was working on the Voyager-Neptune encounter in August of 1989. In her current position, Titan Orbiter Science Team Co-Chair, she coordinates all the Titan science opportunities for the Cassini mission. She's also the group supervisor of the Science Planning Systems Group at JPL, which provides people and processes to integrate, implement, and execute science plans for instruments and missions at JPL. She received her bachelor's degree in physics from Cal State Northridge and her master's degree in astronomy from San Diego State University, where her research specialty was planetary nebulae. She has received numerous awards, including a NASA Medal for Exceptional Service, and is an active public speaker for NASA, JPL, and the Cassini mission, not to mention a founding member of the Cassini Virtual Singers, a group of project staff that rewrites the lyrics to popular melodies and performs them at various project and laboratory functions. Ladies and gentlemen, please join me in welcoming one of my favorite people here at JPL, Trina Ray.
Well, Mark told you everything, so are there any questions? No, just kidding. Well, thanks so much for coming out this evening and joining me at the Von Kármán Lecture Series. It's a pleasure to be here. It's a pleasure to talk about Titan. As Mark says, I've been involved on the mission for many years, mumble, more than a decade years. I've been at JPL many decades, mumble, more than two. And so it's truly been a privilege to work on this mission and learn so much about this fascinating object in the solar system. So to give a little bit more background on the history of Titan exploration, as mentioned, it was discovered by Christian Huygens in 1655. Here's his publication. You can see Saturn running down the middle there, and here's Titan, which you saw on each side. 1900, Sola, actually using a telescope in Europe, took a look at Titan sort of every night, night after night, and every night he saw limb darkening, and so it can't be a feature if the limb is always dark every night, night after night, and so he correctly surmised that Titan has an atmosphere. And then in 1944, Gerard Kuiper, using a telescope in Texas, detected methane. And so that was sort of where we sat as we headed into the 1980s, where we had the Voyager encounters. The Voyager spacecraft, by the way, right here on my right and your left, full-size Voyager spacecraft there. Fantastic mission, as mentioned in the introduction, still one of my favorite experiences of my work career at JPL to have worked on the Voyager-Neptune encounter. So when Voyager got there, they discovered Well, they discovered something big. It wasn't a methane atmosphere. It was actually a nitrogen-dominated atmosphere. The atmosphere of Titan is about 98% nitrogen and 2% methane. And so the methane acts as smog in the atmosphere, and you can't see through it. So they took, 1,000 pictures, and all they got was the top of an orange ball. And so, that's not really the observation you want to end with. But there were some things that they were able to see. You could see a very distinctive northern hemisphere, southern hemisphere difference, also this polar hood, and then of course in the details, very complex haze structure on Titan, and in fact even a detached haze. And so it doesn't take sort of much chemistry or physics when you have now this critical piece of information to realize that sunlight is going to come in to this nitrogen-dominated methane atmosphere. It's going to hit the methane and break that up. A methane atom is 1 carbon and 4 hydrogens, CH4. And when you break that up, it doesn't recombine into methane. So the methane gets broken up, and in fact, there's no chemical process that recreates methane. But the carbons and the hydrogens recombine into various kinds of hydrocarbons, C2H6, ethane, acetylene, propane, all these different things, C3H7, C4H6, all kinds of stuff now is being produced day by day in Titan's atmosphere, and that stuff is not going to stay in the atmosphere. It's going to drift down. And so by the time we sort of fully took in all of this data that came from Voyager, what we were thinking is that there would be global oceans of ethane and methane on the surface of Titan. When you take the surface gravity and the temperature and you work out how thick the nitrogen atmosphere is, we were pretty convinced that there were going to be global oceans of methane and ethane on Titan. And this is the scientific worldview that we had when we built Cassini. And I think it's kind of important to remember that. This is what we knew at the time, and we built Cassini sort of in that frame. And then so you can kind of see the history of how things develop over time, how we answer old questions and open new questions. It's one of the great privileges of working in something like a planetary science community where these things get answered over the decades. So we left the Voyager era. Where did we stand basically on Titan knowledge? Well, basically Titan is the second largest moon in the solar system. Only Ganymede, the large moon of Jupiter, is larger. Titan is actually larger than the planet Mercury. The density is about 1.8 grams per cubic centimeter. Just to remind you, water is 1, rock is 3, and iron is about 5. So you can see that Titan is mostly ice with some rock and iron mixed in. Titan is tidally locked. Now, when I say here Titan is tidally locked, at the time, since we couldn't see down to the surface, it would be more accurate to say we are really, really, really certain that Titan is tidally locked, but we really don't have any evidence for that. So we were pretty sure, though, just the physics of it, that it would be tidally locked. That means one face stays towards Saturn all the time. The whole Saturn system is tilted about 26 degrees, so it's going to have seasons. Saturn travels around the sun in about 30 years, so the seasons are about 7 years long. 7 years for winter, 7 years for spring, 7 years for summer, etc. And Saturn's orbit around the sun is elliptical. It's about a 10% difference between sort of when it's close to Saturn and far from Saturn. We'll talk about how that affects things a little bit later on. We knew the atmospheric constituents now, basically with the nitrogen and a rich array of hydrocarbons. We were able to figure out with the radio occultation, the surface pressure is bitterly cold on Titan, bitterly, bitterly cold, 300 degrees below Fahrenheit, sitting at 94 degrees Kelvin. Water is frozen solid on Titan. When you're walking around on the surface of Titan, you're not walking around on rock, well, a little bit of rock and iron, but it's the water is frozen solid. And this is a good time to mention what will become a theme in this talk. One of my colleagues, Dr. Ralph Lorenz, used this phrase, and I've decided to fall in love with this phrase. Familiar physics with unfamiliar substances. And you'll hear that over and over again in tonight's talk. Because there's just, it's perfect for Titan. And again, at the Voyager era, the surface was obscured by photochemical haze, but with all this hydrocarbon, all this chemistry going on, astrobiologically, a very interesting place. So when we talk about Titan more as an analog for the terrestrial planets. It has a big, thick atmosphere, like Venus. It's a slow rotator, like Venus. The atmosphere is heated from above, like all three of the terrestrial planets. Like Venus, it's got this sort of this gigantic single zonal wind structure going on. It doesn't have a Hadley cell like the Earth with a lot of complex interlatitude atmosphere, but it's kind of one big thing. And there's a deep connection between the surface and the atmosphere. So it is much more interesting to talk about Titan as a planetary analog in the sort of comparative planetology with the terrestrial planets than it is to talk about Titan in comparison to the other icy satellites of the giant planets. Ganymede, Europa, Callisto, Triton. I mean, that's an interesting conversation too, but that's not really the interesting conversation. This one is more interesting. And again, the phrase I've decided to fall in love with, familiar physics, unfamiliar substances. So we go to build the Cassini spacecraft, and as we do at NASA, we put out an announcement of opportunity that says we're going to send a spacecraft to Saturn, and these are the questions we have. For example, here's number 2. Determine the relative amounts and differences of the components of the atmosphere of Titan. Scientists from around the world compete to have instruments put on board the Cassini spacecraft, and they tell us which of these questions they can answer. By the way, this is only one slide of 5 when we talk about the Cassini mission, because there's Saturn, there's the rings, there's the other icy satellites. This is just the Titan slide. And then, of course, when you go to answer question number 2, all of the instruments that have check marks there are ones that could contribute to that question. And that is, in fact, where my job comes in. My job is to get together with the scientists and engineers from all over the world that are on this spacecraft and working on this team, and we talk about every Titan flyby and who is going to get the time and the resources of this precious time. We don't fly by Titan very often, maybe about once a month. The 24 hours right around the flyby is just ridiculously precious in terms of what we can learn about Titan, and the 2 hours around closest approach, even more precious than that, and the 15 minutes right at close approach, yes, we argue about it a lot. No, argue, bad word, sorry. We discuss a lot. I've often said my job is to work with adults and teach them to share. But the beauty of it is this is what I love about my work, is that you're in this room, and it's like the coin of the realm is scientific merit, and everybody has sort of data, logic, and reason on their side, and the discussions are extremely, they move fast, and you have to pay attention, and it's just a pleasure to be part of that puzzle-solving community. I love my job. If I won the lottery today, I'd probably still be here. Wait a minute, I saw my manager somewhere in this office, in this room. Yeah, there he is, yeah. No, so I still want, my salary. I really do. The Cassini spacecraft is fantastic. It's the size of a bus. So here it is over here on the right-hand side of the room. By the way, this is a half-size model. Okay, this is a full-size Voyager spacecraft, and that's a half-size Cassini model, because of course they couldn't put a full-size Cassini model in von Kármán. The spacecraft itself stands, as I mentioned, about 22 feet tall. The high-gain antenna, they're about 13 feet across. When it was launched, it weighed about 6 tons, and most of that was fuel. We had 700 watts when we started the mission, and we've been degrading ever since. And we have a gigantic, huge, whopping, I couldn't believe it when I first came over to Cassini from Voyager. We had 0.5 gigabyte recorder. Gigantic. We'll never fill it up. Yeah. Yeah, I learned my lesson there. For those of you who are younger in the audience, your parents will teach you about this. Income rises, or expenses rise to meet income, right? So in planetary science, we have this very same thing, which is science data rises to meet the size of the SSR. So it was launched in 1997. We had a loop-de-loop around the intersolar system to get out to Saturn in a blistering fast 7 years. So we got out to Saturn in 2004. This is the launch video. I wasn't there. I was actually here working launch. A friend of mine took this picture. Gorgeous. The largest rocket the U.S. was currently launching at night with a cloud deck. And I wasn't there, but I'm not bitter. I have let it go. No, really, I have. I know I sound bitter, but really, I've let it go. It happens. Yeah, that. And can you imagine the day after when he sends you this picture? Yeah, it's just, next time I'm going to the launch, that's all I'm saying. As we had launched the Cassini spacecraft and we're headed, so we finalized the instruments, we finalized the design, everything is done, right? Then we start learning more and more about Titan. Hubble comes out with this great image from their infrared camera, and you could see distinctive features on the surface. This gigantic feature here, which has come to be named Xanadu. Many of the bright and dark features on Titan are named after mythical places, Xanadu, Aslan, that sort of thing. So this is a Xanadu. And then, the Europeans, not to be left out, at the European Southern Observatory in Chile, they started to produce images like this while we were on our way. And every time they looked at Titan, it looks fuzzy. So you think to yourself, this is clouds, but it's not. Every time you come around, the same features are there. They gave them fancy names, the lying H. Where's the dragon head? Here's the dragon head here. The dog with the ball, that sort of thing. And of course, not to be outdone, as Cassini approached, we had to release this image. It said, look, we're good. Lying H, dragon head, dog and ball, we're there. But of course, once we got into orbit, we did quite a bit better. So in addition to the 12 instruments that are on the orbiter, Cassini is somewhat unique in that it was a pathfinder in terms of partnerships with the European Space Agency. So we had partnered early on with the European Space Agency. They were going to create a probe that was we were going to piggyback it out there, and it was going to drift down to the surface, drift down to the atmosphere of Titan, down to the surface. And so there are 6 instruments on the probe, and they've got their stuff and we've got our stuff, and we partnered together. This is one of the first extremely successful partnerships between ESA and NASA for planetary exploration, and in fact is in some ways a pathfinder for the relationships that the Mars community is exploring now on how to partner with ESA. So we piggybacked it out there, and on Christmas Day 2004 we ejected it, and off it went to its rendezvous with Titan on just in the middle of January, just 20 days later or so. Off it goes. Now, of course, it's moving pretty fast, so the first thing that has to happen is that we have to slow the spacecraft down. We went sort of from, I think it was like 20,000 kilometers a second down to 6 or 5. I mean, just a lot in this heat shield. I used to have, wow, I am getting old. I used to have these numbers right on the top of my head. So we were going fast and we slowed down. And I'm sure the data is in there somewhere. It's just not coming to my mouth right now. So we had a parachute where we pulled the back shell off, and then we had a second parachute where it was just a gigantic parachute that allowed us to pull the probe out of the back shell. And the probe now is exposed to the atmosphere of Titan, and it's spinning on its way down, and it's taking pictures. Think of it as a Frisbee that's spinning, and everything's looking off the side, and as it goes down, it's taking these pictures. It's radioing the data back to the Cassini spacecraft, which is then in turn radioing the data back to the Earth. If we stayed under the big chute, though, we only would have gotten to the top couple of percent of Titan's atmosphere, and that's not what we were interested in. So we had to get rid of that parachute, and we had to go ahead and have a third parachute that was much smaller so that we could drift down to the surface. Now remember, when we built Huygens, we didn't know for sure the atmosphere. We had one measurement from one instrument at one moment in time about the atmosphere of Titan, and we built something that had 3 parachutes that had to go off exactly in the right order at the right time to get down to the surface. These were fun reviews to sit in, by the way. And because it's ESA and NASA, these are not just your regular reviews with, people that you see around the lab the whole time. There's NASA director, ESA director sitting there. Good times, good times. And of course, we had no idea what would happen when we actually landed. We didn't know if we would land in the global oceans. Huygens is designed to float for a little while. We didn't know if we'd land on the top of Everest and tumble down. We had no idea. So on the day that these images came back to Earth, and they were coming back to Earth, every couple of minutes, and what do you see? Haze, 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 haze. Not a surprise, right? We knew about that. And then all of a sudden, you start seeing these images, one after the other, of something that you just know right away that this is not your average icy satellite of the outer planets. This is not heavily cratered. This is not, this is different. This is very Earth-like. And to be in that room, I can only imagine how exciting it was. I wasn't there. I was actually at the U.S. Figure Skating Championships, which I go to every year, but that was the hardest decision of my life. to go to the figure skating championships that year instead of to Germany for this. But of course, it sets a very high bar now for any other figure skating championships, right? It's like, I didn't go for the Huygens landing. You think I'm staying for this? No, I'm going. So of course, Titans on ice, they touch my heart. The surface of Titan. So this is a nice image here. So let's just pause for a minute. I mean, this little probe, which, it took a decade to build, it took a decade to get there, and it drifted down through an atmosphere that we weren't even sure we completely understood, and then it landed on this plane and took this picture on a moon, the surface of a moon 1 billion miles away. I mean, it just gives me goosebumps just even to look at it now. And here are these little cobbles in the way. And now remember, again, familiar physics, unfamiliar substances, right? These are little rock or ice cobbles. These are not rocks. So if you were to look at this picture on the Earth or Mars, you would say, oh, well, these are little rocks. No, this is frozen water ice here. And it's obviously rounded because it's been tumbled by liquid. That liquid is ethane and methane. But this is a little frozen water cobble. And just really an exciting time in the Cassini mission. Here's a mosaic of all those images put together. And then here are a couple of close-ups where you can see in detail, appreciate those river channels. Here's the landing strip for the aliens, if you happen to go that way. The large parachute we were under, the stabilization parachute wasn't as stable as the Europeans had hoped for, so they kind of didn't know where Huygens had landed. And in the end, it was a couple of amateur astronomers looking and seeing that these two dark spots there were really these dunes here that actually helped place the Huygens landing site. And you've arrived. Yeah. Literally almost, I weep the fact that this magazine is gone. Nothing but fun from this magazine. So that was the Huygens mission. That was, successfully completed. And there's no question that when we look at the history of the Cassini-Huygens mission to Saturn and Titan, the #1 scientific achievement will be the successful completion of the Huygens mission. But the Cassini orbiter has a lot to say about the Titan flybys. So Cassini gets there in 2004, and we have a 4-year funded prime mission. There are 45 Titan flybys. Every one of these little pictures of Titan is a Titan flyby. So you could see year 3 was very intense for Titan flybys. This is when we were cranking the orbits up. We got to fly by Titan all the time. Then we had a fully funded 2-year extended mission to study mostly the equinox, and we got another 26 Titan flybys. And again, what I do is I work with the scientists to decide what we're going to do on every one of those flybys and choreograph it. Here's what a flyby looks like. It starts out about 24 hours out, and we are sort of far away from Titan, and Titan is slowly growing in the field of view. So of course we're using our optical remote sensing, the cameras, to look at Titan. Sometimes we trade between them because they want to look at different things. This is the white square is the camera, the visible camera. The red one here is an infrared observation. Then Titan is slowly growing in the field of view every hour that we pass. Pretty soon it's so big you can't see it in the VIMS field of view, so you have to do a 3x2 mosaic. There's the Huygens landing site, by the way, right there. Now we've handed off to the high-resolution imaging camera, and it's trying to do as much as it can to get a mosaic. Then we're spinning the spacecraft around so that the radar instrument can get some data, and then here, right at close approach, zoom. That's our radar SAR swath right there. And then on the way out, we do some radiometry and try to get some surface information using radar because, of course, the sun's on the other side. We can't use the cameras now. And then finally, we study the atmosphere of Titan. And all the Titan flybys generally have that flavor to them. And we discuss very strongly that central time period and who's going to get it for what science. And so, like I said, good times. So I wanted to throw in a slide that tells you a little bit about the instruments on Cassini and what they teach you about Titan. So a little cartoon here. This is a cartoon of Titan showing the atmosphere and the surface and perhaps a methane sea here. So of course, on every flyby of Titan, all of the instruments that are, we call them the MAPS instruments, the magnetometer, the dust detector, all those instruments, they get data every time we fly by Titan. So they like to fly by when Titan, they like to fly by on the inside of Titan relative to Saturn, on the outside, they like to fly by above and below, but no matter what, they get data every time. Occasionally, we have a flyby that is so deep that it swoops through the atmosphere of Titan, and we're able to sample the upper atmosphere with Titan with the ion and neutral mass spectrometer. Those are very exciting flybys. We have to position the spacecraft just right so that the INMS instrument is able to pull in some of Titan's atmosphere and sample it. Now that only gets you, though, the top part of Titan's atmosphere. That gives you maybe 1,200 down to 900. If you want to go deeper, you have to watch the sun as it drifts behind Titan's atmosphere, and the UV instrument does that, and that will penetrate down to about 325, just a little bit above the haze. If you want to go deeper than that, you have to have an instrument that is called radio science. Radio science sends a communication signal back to the Earth, and so that communication signal goes through the atmosphere of Titan, and as Earth drifts behind Titan, you can track that radio signal all the way to the surface. So this goes all the way to the surface, and in fact, this is the instrument that gives you the temperature and density profile, and in fact, it was the radio science occultation on the Voyager flyby that helped inform the entire atmospheric model that Huygens used for the work that they did. Let's see. Of course, if you want to look at the surface of Titan, which who doesn't, right? Voyager flew by and took like 1,000 pictures of an orange ball. We're not going to make that mistake. You have to go in long wavelengths. So we have 3 instruments that specifically designed to look at the surface. If you look when the light is behind, if you look in your eyes, you kind of get that orange ball still, or if you look at the filter that mimics your eyes, you still get the orange ball. But if you look in the filter that's in the methane window, you can see down to the, if there's clouds, you're looking at the surface, but clouds are in the way, so you can see the clouds. And of course, you can see the surface with the camera and the radar instrument. So it's the long wavelength radiation that gets you to the surface. Additionally, the long wavelength radiation is the stuff that can escape. So the composite infrared spectrometer, for example, can look at the long wavelength radiation that's coming from the surface of Titan, and it can tell you it's 94 degrees Kelvin, and oh, by the way, at the poles it's only a couple of degrees different than 94. So that's the sort of information that you can get there. Also, the radar instrument can look at this long wavelength radiation coming up just passively, and they can tell you things like the dielectric constant of the surface, that sort of stuff. Now, there is another way that we use the radio science instrument. It's a little bit trickier. What we do there is we take that communications link between the spacecraft and the Earth, and we make it a two-way link. So it's like a really finely tuned rubber band. And then as Cassini flies by Titan, sometimes when Titan is close to Saturn, sometimes when Titan is far away from Saturn, sometimes up and down, sometimes side to side, when you put all these flybys together, and the radio science really gets this, you know exactly how much Titan tugged on the spacecraft, and then that lets you learn about the interior of Titan. So that's kind of a little overview of kind of how the instruments on Cassini contribute to our knowledge. I put this slide together last night at like 2 in the morning, and I love this slide. I'm tickled pink about this slide. I'm going to make it even better. So next, if you ever see me again, I got nothing but ideas on how to improve this slide. It was 2 in the morning. You can only do so much, you know, when you have these ideas. Let's see. So this is our current best map of Titan that comes from the camera. This is the visual camera, but it looks it has one filter in the infrared or near infrared. I'm going to use this map a bit as a guide as we talk about all the other features on Titan. So I want to kind of give you some tour guidepost. Note that in the central equatorial region, which is between plus and minus 30 degrees, you see dramatic dark and light albedo features. These are the ones that have those names of the mythical places. Here's Xanadu, Aslan, Quivira, all that. So these are the equatorial regions. Up here, you can see the camera has not filled in all this territory yet because we just got to northern. We just passed equinox, so it's been pitch black in the north, just like here on the Earth. It's pitch black in the north until, it's time for northern summer. So the camera is just now filling in this area up here, as is the visual and infrared mapping spectrometer. Now, this image in your eye kind of doesn't look as interesting. Like it's like, oh, that other one is higher resolution. Why do you even care about this one? The interesting thing about this one is that this isn't just one image. This is simultaneously 250 images at a variety of spectral wavelengths. So this is a spectral imager. So you get, if you want to look just at the 5 micron region, you can have an image. If you want to look at the 2 micron region, you can have an image. And if you want to look at the 1 point, you can have an image. And if you want to put the 3 together with a color filter, you can do that. And then when you do that, oh my gosh, certain things really jump out at you, right? These 5 micron bright regions down here are really dramatic. So this is the information that tells us that, for example, the surface of Titan is covered in hydrocarbon goo. I mean, it gives you composition information. It comes from the VIMS instrument. And then, of course, here's our current map of the radar coverage. Remember, radar was that little strip in the movie, right at close approach, plus or minus 15 minutes. You just get a little strip each time, you just get zoop, that's it. And over the course of time, we build up this map. I know to you guys, this map looks like, wow, you really, you've got a lot of holes there. But for those of us who've been on the mission for a decade, I'm like, yeah, look at all the radar data. We have so much coverage, it's crazy. And of course, you want to get to the interesting places like Xanadu. We want to get up to, the features at the north. But additionally, radar also wants to have sort of these crisscrossing flybys so that they can help constrain the shape model. So let me talk to you first about the dunes. Those are those bright and dark features that we saw that are mostly contained between plus or minus 30 degrees. These are dunes. Dunes on Titan. So just think of the dunes of the Namibian desert, okay? These here are 150 meters high, 1 to 2 kilometers apart, and they go on for hundreds to thousands of kilometers. They're little pieces of ice water covered in hydrocarbon goo. Think of it maybe as coffee grounds. And they're piled up, and the wind pushes them back and forth until they're in these long stretches. Here's a close-up image from the radar. You can see here that the wind must have been moving in this direction because as the dunes came in, they had to deviate around this little facula here, which is higher. This little piece here is higher than the rest of it. You can see here on the leeward side that the dunes don't reform until a little bit later, so the winds must be coming in this direction. In fact, you could take every dune on Titan and lay out how the winds are moving at that particular place. All the winds at the surface are moving west to east. Here's another close-up of the dunes coming in and hitting a higher feature. And another. Spectacular. Familiar physics, unfamiliar composition, right? It's not sand, right, on the Earth. So, this is like one of these important things sort of to take in, this Earth-like dichotomy. Familiar physics, unfamiliar substances, like I said. So on the Earth, you have mountains. The mountains are made out of rock, and when you have volcanoes, you have molten rock that oozes out onto the surface. Over time, the Earth's atmosphere weathers the mountains, and pieces of the rock fall off. And those big boulders fall down, they fall into streams of water, and they get tumbled around until they become pebbles. We saw pebbles on the Huygens image. Then they break up into little tiny pieces and become sand. And the sand dries out, and the winds of the Earth blow the sand around. Okay, that's the Earth. On Titan, the thing you walk around on is made out of water ice. So it's water ice that the mountains are made out of. When you have a volcano, it's molten. It's water. It's H2O that oozes out on the surface of Titan. And when rocks fall off of mountains on Titan and tumble around, little ice chips are what falls off. And then those get covered in this ever-present hydrocarbon goo. And then that's what dries out and makes the dunes. And the dunes cover the whole equator. They go from side to side. There almost isn't a spot on there that isn't covered in dunes except for Xanadu. And how interesting is that? Why are there no dunes in Xanadu? So it's spectacular. And if you don't believe me, picture of Titan dunes, picture of Earth dunes. Titan dunes, Earth dunes. This is the Namibian desert. So already we've learned something spectacular about Titan and how Earth-like it is. But wait, there's more. So the north, right? So we get there, and what happens? The cameras can't see the north. So from their point of view, it's all black, and they can't tell you anything about it. Radar does its first several flybys, and they're doing equatorial swaths, right? And then all of a sudden, here comes T16. And we go straight across here, and we see nothing but lakes. And we're like, yes, liquid on the surface of Titan. And now remember, familiar physics, unfamiliar substances. Boy, I was in love with this phrase until I keep messing it up. Familiar physics, unfamiliar substances. The lakes on Titan are not made out of water. The water's frozen solid, right? The lakes on Titan are made out of methane and ethane, natural gas. You know, if you think Saudi Arabia has a lot of natural gas, wait till you get a load of the Titan inventory. Maybe we should be asking, this is how we need to get funding for NASA. Okay. It'd be too hard to get it back. Okay. So here, and look at these. These are a whole bunch of little lakes here. Some of the lakes have started to dry up. Then there are these giant things here that we've only had a swath or two. I do want to point out also the south, but I'll talk about that in a minute. So let's just pause here and take in this picture. Okay, this is a close-up of those lakes. Just look at that. Look at this little river channel that's dumping out into Nigeria. And look at this one. You know, just imagine to yourself what Lake Mead looks like from above, and then look at this. And look at how black this is. Now remember, this is coming from radar data, so that we know it's liquid because the radar data is bouncing it away. So that these dark, this is deep, more than 13 centimeters, it's deep. These here are much shallower. And look at the yeah, it's awesome. What can I say? Not that there's a friendly rivalry sort of between Mars and the outer planets here at the lab, and if you're not familiar with it, it's a friendly rivalry. I enjoy this rivalry when it's sort of Titan versus Mars. It's like, you can put up your most Earth-like thing, and then I put up my most Earth-like thing, and then you put yours, and pretty soon I get to, standing bodies of liquid on the surface. I'm like, I win. But it's friendly. It's all friendly. We love Mars. By the way, this is a picture taken from the Visual and Infrared Mapping Spectrometer. What they did is they set up specifically an image that the sun was in the spot, that when the sunlight hit the surface of, I think it was not Kármán, I think it was it was Kármán, I'm pretty sure. It would hit the surface of the lake and you'd get a spectral glint, spectral reflection back to the camera. They took this picture and set it up, and I can tell you there was cheering that day on the VIMS ops team when they caught that glint off of that lake. So now let me talk about the one lake that's in the south. It's named Ontario Lacus. So it's in fact roughly the size of the Lake Ontario. Here it is here. It looks very lake-like. It's sort of by itself. There's not a whole bunch of lakes around it. This is the radar image there, zoomed in, and then I'm going to go ahead and zoom in one more time. You could just kind of look at this lake, and you can see similarities to lakes on the Earth. Here's a picture taken at the edge of Lake Michigan, and you can see it has a shoreline that's very similar to the edge of Ontario Lacus. Here's a river channel that's oozing silt into the lake. Here's a river channel on Titan with stuff and silt oozing into the lake. Here's a little sort of a bay with intrusions. This is Lake Mead. So beaches, deltas, flooded canyons, how fantastic is that? This is where Ontario Lacus is, by the way, on the big map to orient you. So spectacular, right? And I think, let me go back 2 slides because I didn't mention this at the time. So the lakes cover about 1% of the surface of Titan. They're filled with methane and ethane. And when we say they're filled with methane and ethane, we know that there's liquid ethane in Ontario Lacus. We did an observation that was very specific to figure that out. We do the math about the temperatures and the volumes and all these sorts of things, and we just figure that the methane also has to be liquid. But because we're looking through this atmosphere that's filled with methane, it confuses our instruments. So we don't have a definitive detection of liquid methane, but it has to be there. Just the volumes of the lakes and all that and we have liquid ethane, and we know the temperatures. So, but you could see immediately that there's a dramatic difference between the North Pole and the South Pole. And what we think is happening there is hearkening back to what I mentioned to you guys early in the talk. Remember I said that Saturn's orbit around the sun is elliptical, and it spends 10%, about a 10% difference, which is quite dramatic. So the southern summers are short and strong. And so most of the lakes have evaporated here. So in the south is where you have the short, strong southern summer. Wow, say that 5 times fast. Short, strong southern summer. But here's the interesting thing. Just like the Earth spins like a top but precesses, Saturn, the whole Saturn system spins like a top but it precesses. In 30,000 years, this will switch, and the northern summer will be short and intense. And so we think, if only we had a spacecraft that would go 30,000 years, and we were here to look at the data, we think that a lot of the methane and ethane would move to the north, or move to the south, because you would have these, it would all dry up in the north. And isn't that cool, though, that just like on the Earth, you have these cycles. You have daily cycles, you have yearly cycles, you have precessional millennial cycles. How exciting is that? And let me get back to... So Xanadu, I've mentioned it a couple of times. How interesting is Xanadu? This is the radar SAR swath over Xanadu here. There's going to be a few little close-ups here. Xanadu is almost duneless. It's clearly bright in radar. Now remember, radar instruments blast the surface with the radar data, and if the surface is flat and smooth, the radar signal bounces away and you get very little coming back. When you get signal coming back, it's because the surface is jumbled, or perhaps it's because the surface is perfectly aligned so that it reflects right back in your face. So, when you have something bright like this in radar, it usually means there's a lot of interesting terrain there. And here are these little jumbled mountain regions. So all that jumbly terrain reflects the radar signal back to us. So again, all of Xanadu is quite bright. There were some river channels earlier that they highlighted for you. We've got these little, strikingly, there's straight things. Anytime you have straight things on the surface, you kind of think to yourself mountain ranges, things like that. There are these regions that are low. Maybe they were like dried lakes. We're not sure. I mean, this is the great thing. Xanadu is still fascinating to us, even though we've been studying it now for years. All of Titan is fascinating to us. And I think that's it with the, and this is the east coast of Xanadu. So I just want to also mention, hearkening back to something I said before, this is that the VIMS, the Visual and Infrared Mapping Spectrometer. So this is that camera that looks in the infrared in those two really bright regions. I'm going to zoom in here on Haute Regio. So here's the bright 5-micron region, and when we did a radar pass here, you can see that it's extremely interesting flows, little river channels, or some kind of channel coming into it we've drawn them out here for your eyes, makes it easier to see. Absolutely fascinating. What is causing this? Maybe there's a activity underneath and something's oozing out onto the surface that makes it chemically different. Maybe it's a crater. Maybe it's, who knows? But we know that it's interesting and we know we need to study it more. And that's the great thing about working on a mission for this long with a territory that is so interesting, is that you almost can't swing a dead cat without hitting something interesting, Volcanoes, right? I've talked about dunes, I've talked about lakes, I've talked about rivers. What about volcanoes? It's an obvious question because I mentioned that methane gets broken up by the sunlight and doesn't recombine. So we have methane in the atmosphere right now. Where's the methane coming from? Volcanoes are a good answer. If there's volcanoes that are resupplying the methane, that makes sense to us. So here was one of our very first flybys. We flew by Titan, and look at this picture. Oh my gosh, this looks like a pancake dome, just like it is on Venus. Is there a high pitching, whizzing thing? Yeah. Okay. Oh, and it's gone. See, if I just would have been patient, my number one problem, not enough patience. So look at this. It looks just like a pancake dome, and then there's these flows out here. This is probably a volcano. Well, in a later radar flyby, we went over this territory again, and we were able to get that data that tells you the heights of things. And what we expected was this is low, and then we get higher, it gets jumbled, and then zoop, a high pancake, zoop, straight across. That's not what this is at all. All of this is low. This is like a mountain range in here. This is a deep spot. This is all, So that one's gone. And in fact, we've had several of those. It's really hard. If you don't have like a volcano spitting in your face, it's really hard sometimes to pick that that's a volcano versus that's some other structure in the surface. This is currently our best volcano candidate. The nice thing about this one is when we did the SAR topo that told us the topography, oh look, the high thing is high and the flows are low. Yes. This is probably our best candidate right now for a cryovolcano. And again, we really kind of need to have these volcanoes so that we can resupply the atmosphere. It's an interesting mystery still. And then also just remember, on Titan, the rocks are made out of water ice. So when there's a volcano, it's molten ice or liquid water that comes out onto the surface. Titan has very few craters, of course. There's a big, thick atmosphere that could wipe out, covered with dunes, craters, all that sort of stuff. We have lakes that are evaporating. We have all kinds of stuff. We might have volcanoes. So there are very few craters. Most of them are in the equatorial region. Maybe that means that there's some sort of selection effect in terms of they all have similar formation stories. Maybe that means that there's something else going on that's wiping them out in other places. But nonetheless, there's currently 8, although there's maybe another dozen or so that are sort of to be reviewed and approved. This is the large crater here, Menreva. You can see that usually pretty easy in the maps. It kind of draws your eye. It's pretty easy to see. This is a nice close-up here. I just like this image because this is the top edge of Xanadu. Here are the dunes, and then the dunes hit the crater. This is the crater Sinlap, and it just, boom, stops. It's beautiful stuff, so you can really learn a lot from the radar images. We do have mountains on Titan. Mountains on Titan are not the Rocky Mountains, okay? No, the mountains on Titan are like the Appalachian Mountains. They're kind of short. They're maybe a kilometer or two high. But whenever you have, straight line things like this, it just tells you that there's some kind of mountain forming process going on. We're not exactly sure what it is. Maybe like Titan is cooling, and as it's cooling, it kind of wrinkles up the surface a little bit. That's one explanation for things like this, but there are others. We don't have a lot of mountains, but they're definitely there. Most of them run east-west. There are a few that run sort of north-south. These are the 3 that I have showing you there. And then, because Cassini is the gift that just keeps on giving, we flew by Titan in December of last year, and the radar team took an image, and they don't know what it is. They look at it and they say, well, there's a lot of grooved straight lines. There's all of this jumbled stuff, more straight. We don't know what this is. And isn't that a cool place to be? That we've done 80 flybys of Titan, and we're still finding territory that we don't understand. How terrific is that? Oh, and I didn't put my little circle. Huh. Well, not only is it unknown territory, I don't know where it is. Actually, I don't. I would tell you where it is, but I'm right now just drawing a blank. It's somewhere on Titan is where it is. Like I said, Titan, the gift that just keeps on giving. So September of last year, we took a picture of Titan. We've been watching for clouds. We've had clouds in the south. The whole north is dark, so we haven't been able to see any clouds in the north if it's been there. The camera comes along one day on September 27th and takes a picture, and whammo, a huge cloud in the equatorial region. We had very few in the equatorial region. This cloud system spread out around the entire moon. It lasted for days. And then we took a little snapshot. We've started this new thing. We try to look at Titan every time we can and just take a 30-minute snapshot so that we can capture these sorts of events and learn about them. And so what happened was we had extensive surface change. So this is the image before. I draw your attention to this area here, and here's after. Before, after. Before, you can see the dragon head. After, you can't. Wow. Yeah, it's cool. There's not much else to say. Rapid, extensive surface change. I mean, this territory is the size of Arizona and New Mexico and Utah combined. It's huge. These are like rainstorms in the desert, right? They come out of nowhere, there's boom, flash flood, wets everything, and then it dries up. Of course, now we've been looking at this area recently, and it's slowly gone back to its pre-rainstorm albedos. So that brings us to talking a little bit about the atmosphere. The atmosphere is very interesting to, by the way, that high-pitched hum is still there, people. If you guys, I don't know if you could do anything, but is it me? Is there anything I need to do? Okay. I thought I'd offer. Because if it was like, oh, just move that, I could do that. So remember, the sunlight hits the methane, and the methane, we still have methane in the atmosphere, so there must be something supplying the methane. That methane breaks up into all these little hydrocarbons. These hydrocarbons just sort of sit up there. They combine with each other. They're very small little, molecule-sized things, and then pretty soon they clump together. They fall as dust down to the surface, and that becomes your hydrocarbon goo that covers the little chips of ice and that sort of thing. So we have this cycle, which lends itself to having this very high level of haze, which I showed you in the Voyager pictures. This is the haze that causes that detached haze. But we also have lakes on Titan. The lakes are filled with methane and ethane, and that evaporates. And there are clouds. The clouds form. You've seen the clouds, and then the clouds rain. You've seen the rain, and the rain flash floods into the river channels, and then out onto the plains, and that's in fact where we think that Huygens landed, in one of these plains. That the river. You saw that river channel as it came down, and then all these little bumbled, tumbled bits of water ice. So it all kind of hangs together that way. Here are some nice. A nice set of collage, sort of the pictures. These are some clouds at the south pole of Titan. These were little rainstorm clouds we saw back in 2005, 2006 at the south pole. These are some mid-latitude clouds. We see these often in about minus 35 degrees latitude. They sort of appear all the time at the same mid-latitude. That kind of makes us think that maybe there's a vent there. Maybe it's not a volcano. Maybe there's just a methane vent that's constantly poofing methane up and creating these little mid-latitude streaks that then get blown to the east by Titan's atmosphere. Of course, now that we have light in the north, we've seen the giant clouds in the north. And here's a nice, yes, I know, scientific graphs. Hold your seats. It's okay. It's just a plot. It's very easy. This is latitude, this is time, okay? So the giant storm that I showed you, which happened in the middle of, 2011, here it is. See, it was extended in latitude. All those little mid-latitude streaks here they all are. July 2007, boom, there was a little mid-latitude streak. Those southern summer clouds here, and of course the northern clouds here. But remember, you really have to understand what are your biases and your selection effects when you look at data. It's very important that scientists learn how to do that. You should always be asking yourself, well, why are there no clouds here? Is it because there are no why do I have no data here? Is it because there were no clouds here? Or maybe it's because the camera couldn't see the North Pole here. And there were clouds there the whole time and we just couldn't see them. So you always have to remember stuff like that. Now we're not seeing clouds in the south. Maybe we're not seeing clouds in the south because now we can't see the south. Maybe the clouds in the south stay the whole time. So you always have to understand what are your biases when you look at data. But anyway, this is a nice little plot of data there that shows the distribution of clouds. 54. This is a close-up picture of that detached haze of Titan, now taken by the Cassini spacecraft instead of the Voyager spacecraft. When the Voyager spacecraft flew by about 30 years ago, the detached haze was sitting at about 350 kilometers high. When Cassini flew by in 2004 and started orbiting Saturn all the time, the haze was sitting at 500. And we have actually watched, as we've gone from summer to spring, we've watched the haze fall. And Voyager flew by 30 years ago, and you might remember 30 years is the time it takes Saturn to go around the Earth. So Voyager flew by at the equinox, and it, of course, measured the haze at 350 kilometers. So what a nice scientific result there. Again, just like the Earth, we have meteorological things happening on day to day, on week to week, year to year. These things are happening. Titan is a fascinating analog for studying Earth processes. The chemistry, we could have a whole talk about the chemistry in Titan's atmosphere. It's just crazy complex in terms of what happens. I like to show this diagram quickly. If you were to take the ion and neutral mass spectrometer that is on Cassini, and if you were to fly by Venus, these are the ions that you would see, or the Earth, this is what you'd see, and this is what you see at Titan. Okay, this is so I'm not making it up, okay? This is a chemically interesting place. If you want to study interesting hydrocarbon chemistry, you should be studying Titan. Now, we can't really, I mean, the surface is fascinating. Oh my gosh, rivers and seas and dunes, oh my. You know, the atmosphere is fascinating. There's really a lot to talk about, but we've only got so much time. I did at least want to mention a little bit about sort of Titan's situation in the Saturn system. So Saturn is a giant gas planet. It has a strong magnetic field, and that magnetic field rotates with the planet. The planet rotates about once every 10 hours. And the material that's out there, the ionized material, is Saturn's magnetic field picks that up and sweeps it along once every 10 hours around Saturn. Titan only moves orbits once every 16 days. So basically, Titan is getting hit in the back of its head constantly by this stuff from Saturn that Saturn has locked in, smacking it in the back of the head constantly. So from Titan's point of view, there's this constant pressure of the plasma that's getting pushed on the back of its head. And so in front of its face, because remember, it sort of constantly moves around tidally locked. So, it's always, this is the leading edge there is always the leading edge. And it's always in this sort of this, it never sees anything hitting it in the face. And so it's constantly in this situation. And here's a nice diagram from with showing you how those field lines from Saturn just wrap around Titan. So you might ask me, it's a very reasonable question. We've been there for 7 years, 8 years, 9 years. Does Titan have a magnetic field? This is an important piece of information. Do you know the answer? Then we don't. Because, when we fly by Titan, what we see is Saturn's stinking magnetic field covering the whole thing. We did try. We were very lucky that we have a spacecraft team that is really willing to work hard and to work with us when we have big questions that we need help answering. So we told them, I know normally you fly by Titan at 1,000 kilometers, maybe 960, but if you could get down low, just could you get us like 800 or 850? Could you get us down there? We might get beneath the ionosphere of Titan. We might be able to see if Titan itself has a magnetic field. We know that whatever it is small, because if it was big enough, we would see it. So whatever it is small, but we can't see it in all the soup of Saturn. And so the spacecraft team worked really hard. They worked for, I think one of the estimates I heard from Julie Webster, the spacecraft manager, they put in 5,000 hours of analysis. And they figured out how to get a flyby of Titan that was 880 kilometers. And we got down there and we were still in the soup. It was a great try from them, though. It was really fantastic. We really appreciate the fact that they worked with us. Actually, I'm going to take questions at the end, Tessa, but I'll come to you first. And the interior of Titan, another basic question, right? You guys should be able to stand here and say, okay, Trina, tell us about the interior of Titan. You've flown by a whole bunch of times. What do you know? Well, so the radio science team told us that if we flew by 4 times, and if the 4 times were just really good, like Titan was close to Saturn and Titan was far away from Saturn. That was 2 of them. And then one time when Titan is close, fly by equatorially, and one time when Titan is close, fly by sort of up and down. And so when you're far, do that. If you do that, 4 flybys, we can tell you about the interior of Titan. Well, that turned out not to be the case. Titan's interior is more complex than that. So he said, okay, give us 2 more flybys. 2 more flybys and we've got it. And so we gave him 2 more flybys. And Titan's interior is more complex than that. And so now they said, give us 6 more flybys, at which point we said, hold on a sec. Perhaps this is a question that cannot be answered by Cassini. Perhaps this is a question that can only be answered by a Titan orbiter. But we'll do our best. So in the Solstice mission, they have another 5 chances to get gravity data. But currently, our understanding is that Titan is not fully differentiated, that Titan is a mix of ice and rock and iron, but it's not like the iron has sunk to the center and then the rock and then the ice. It's sort of this mush, then surrounded by some frozen water, then a liquid water layer, and then some more frozen, and then the surface, and then the atmosphere. And when I say currently that is our best understanding, I truly mean currently, and this changes often. I literally got an email yesterday that some new guy has a new idea about it being differentiated, and so this is our understanding as of 48 hours ago. I have not had a chance to read the new paper, but at least 48 hours ago, this is where we stood. And that's actually pretty exciting, too. The global shape model, another one of these pieces of information that comes from all of the radio science and the radar data. And Titan is essentially squished. It's shorter at the poles than the average, and the equator kind of bulges out. But the most fascinating thing in this diagram is the fact that Xanadu, not a continent at all. Xanadu is a giant depression. Who would have thought that? How awesome is that? I heard this long ago when I was in college. The most interesting thing a scientist can say is not "Eureka, I found it." The most interesting thing a scientist can say is, "Huh, that's funny," and it's true. It's dead true. And so with that, let me just finish up here with a few slides. I want to. Cassini's still going strong. We had our prime mission. Here's the Saturn's year. We got there in just after winter in the north. We had the prime mission. We had a 2-year funded equinox mission, and we're currently executing the solstice mission, which will take us out to 2017. We get another 56 Titan flybys. Yeah. And my team is busily planning each and every one of those. There are open questions about Titan, lest you think that Cassini's answered them all. There is no way. You know, what happened to the oceans? I mean, actually, the people that did that work back after Voyager, they were pretty smart, and there should be oceans. You know, why does Titan even have an atmosphere? Where's the methane coming from? Have we always had methane? Actually, really, where's the nitrogen come from? You know, there's just a lot of questions. I get this one a lot. We can talk about that if we have time in the questions. NASA is currently in the midst of what we call, we have competed missions. So we have Discovery, New Frontiers, and flagship missions. Discovery, New Frontiers, so there's small, medium, large. The large ones are usually directed, but the small and medium missions are usually competed. And currently we are in the midst of a competition. And there are 3 finalists. There is a finalist from JPL that's going to explore Mars and the tectonics of Mars. There's a mission from Goddard that's going to go to a comet and then to another comet. But of course, since this is a Titan talk, I just thought I'd mention here that there is one of the finalists is a mission from APL that's going to have a lander that's going to float on the large sea of Titan. It's the Titan Mare Explorer. It'll last for a couple of months. Oh, actually, it's going to Ligeia Mare. And it'll be there in northern summer, so it can directly contact the Earth. And how exciting would that be? Actually, any 3 of those missions, it would be fantastic. I only wish NASA had enough funding for all of them because they're all great. But of course, Titan one sort of has my heart. And so I'd like to close then with this slide here. And I hope that you've enjoyed the talk tonight. I hope that some of the mysteries of Titan have been revealed to you. I hope that you appreciate more how remarkably Earth-like Titan is and how much we can learn about the Earth by studying Titan. I hope that you are totally jazzed by how awesome Cassini is, and it is just rocking it day after day after day. It's an extraordinary spacecraft, returning extraordinary science, and hopefully will continue to do so until 2017. It is an utter privilege to work on the team and here at JPL, and I thank all of my colleagues, in particular all the scientists who did all this great work, that all I've done is share their results with you here tonight. And with that, I will close and take questions. So I promised first question. Oh, and also if you're going to ask a question, could you please come up to the mic here in the center? They're filming this, and they're also broadcasting it live on the Ustream. And so no one can hear the question unless you're at the mic. Is it working? Yeah, looks good.
Okay.
Or sounds good.
Actually, I have 4 questions.
4 questions?
Taking notes.
How about ask one, and then we could cycle you back,
Okay.
so everybody gets a chance.
Okay, I'm going to ask the one that was most recently that I noted.
Okay.
And it was about the graph that you had, the SLT graph.
Okay.
And you had X expressed in R and X expressed in R.
Saturn local time, and then,
Okay,
the
now-
X is towards Saturn. Could we bring up the slides again, actually? Is that okay?
So that was axis?
So what it is
Those were the axes?
in the magnetic, right, so in the magnetic, when you're talking about the magnetic field of Saturn,
Yes.
those folks, let me just go back to that real quick. There it was. So when you're talking about those folks, what they like to do is they like to, SLT stands for Saturn local time,
Okay.
and what they like to do is have X be towards Titan, Z be straight up, and Y, I think, is in the direction of motion. Now, I'm not going to swear to this, because these are the magnetic people, and they do odd things, but I'm pretty sure that's how that works.
So it's for orientation.
Yeah, yes, it's orientation, but it's this orientation.
Yes.
So I think X points this way,
Right.
Y points that way, and Z points out. And of course, as Titan orbits, it constantly changes. But they like that configuration because then they could really study these and take out the orbit of Titan.
Right. Okay.
Okay?
Thank you.
All right. And so does anybody else want to ask a question? And then we can cycle back for sure if there's no more other questions. Could you come to the mic? Would that be okay? Thanks.
Okay, I have a three-part question.
Oh, okay. Could you ask one, and then we could cycle back? Well, if it's three parts, let me at least hear the first one.
Okay, in regard to the thylons, i.e. Molecular precipitation, has the actual methane increased due to the fact that maybe there's more going through cryovolcano?
So I know of no data set that we have that is indicating an increase in methane. We measure methane in the atmosphere with our occultations, and we get occultations at particular times and at particular latitudes. And so there's a lot of variables to understand that, but to my understanding, we don't have any trend of increasing methane or decreasing methane.
Secondly,
Want to try your second one?
Secondly of all, is the Moon Hyperion locked in the same way that Titan is locked to Saturn?
No, it is not. Hyperion is a chaotic rotator. It's further out from Saturn. So if you know the little acronym Dr. THIP, T-H-I-P is Titan, Hyperion, Iapetus Phoebe. It's further out and it is not tidally locked. It's a chaotic rotator.
And third,
You never know with questions. At a von Kármán lecture series, believe me, there are people in this audience who could ask me questions and I wouldn't know.
okay, and thirdly of all, has the Cassini orbiter actually located more cryovolcanoes in the initial mission?
We have, but every time we locate a cryovolcano candidate, somebody brings in new data that knocks it down. So currently we have, our best is the one that I showed. But you know, after a while, we're getting better. So so far, just the one. But we've had several candidates that have come and gone.
Thank you.
Thank you. Any other questions? Yes? Okay, I'm ready, Jed. I'm ready.
Okay, I have one-part question. You'd expect ammoniated water.
Yes.
But anybody looking for any possibility of finding the ammoniation, anything like that in the water? Or is that a spectrally difficult
So that's
thing?
going to be at the surface, and we're not doing, actually that's in the ocean underneath, really. And we don't have chemical analysis of the ocean underneath. What we have is gravity data. What about ammonia on the surface? I'm channeling Jason Barnes right now. He's got the VIMS. I don't think he's talked a lot about ammonia on the surface, at least not that I'm aware of. At least it's not a big topic of conversation. Sure? Oh, yeah. Thanks, Mark. We have questions from the Ustream. Go ahead.
Okay. What is the average wind speed on Titan?
Slow. It's a big piece of atmosphere. It's like Venus. It's a slow rotator. It's heated from above. I think its average is less than like a meter per second, so it's slow. Occasionally there are bursts in the global circulation models that burst above a meter per second, but it's generally slow. It's not a fast wind.
And you mentioned that the average temperature is 94 degree Kelvin?
On the surface?
On the surface, and just a few degrees less at the poles? Is that common
is it less
for...
at the pole? One pole is less and one pole is more, right? Let me just think.
Okay.
I've seen that graph many times. Many times. It's right there. The equator is the warmest. I think they both get cooler at the poles. But boy, I'm not going to swear to that. I'd have to check that out.
Is that a common...
That comes from the Sears instrument if you want to look it up online. They're the ones who tell you the surface temperature.
Is that a common occurrence where a temperature is pretty stable throughout the entire planet or moon?
Well, on something like this, where you have one giant atmospheric thing, so it's the same with Venus, right? Not on the Earth, where you have the Hadley cells and you have the this and the that, but on Venus and on Titan, where it's just sort of one big zonal atmospheric thing, yeah, you should even out the temperatures a lot. There should not be big differences.
Okay, thanks.
And we have a question here from the Ustream. Where did the high concentration of carbon on Titan come from? High concentration of carbon. Let me just detangle this question. So first of all, do I agree that there's a high concentration of carbon? Well, so I don't think there's any more carbon than you sort of expect in the solar. So you would expect in the solar system, the closer that you got to the sun, you expect things like planets to be made out of rock and iron and that sort of thing. And as you get to the outer solar system, you expect increases in the ices. And by the ices, I mean the 4 big ices: ammonia, methane, water, and carbon dioxide. So you're going to have, just in general in the outer planets, you're going to have more carbon. But it is a question. I mean, there is a lot of methane, and it breaks up in the atmosphere. So why do we still have methane is a question. And I think it's still an open question as to what is the history of methane on Titan's, in Titan's, little place in the solar system formation. But I'm not sure if there's a abundantly out of range carbon concentration. I just think it's what the carbon is doing that is more interesting.
You mentioned the Huygens mission. Were there any new discoveries, things we did not know about before the Huygens? What did it add?
Yeah, no, I mean, so remember.
Yeah, we did not mention that here.
Yeah, well, yeah, so when we did not know, when we built Huygens, we didn't even know what the surface looked like. So when we got those images of the rain, all that stuff, yeah. And Huygens has given us one piece of ground truth, right? We have one observation that goes all the way from the surface, or the top of the atmosphere, all the way to the surface. We have the temperature, we have the density, we have the electrons, we have everything, top to bottom. And that is informing all of the orbiter instruments as we build these models. We build these models, which we use the information like from the solar occultation, all that kind of stuff. But every one of those models has got to produce at least the Huygens atmospheric profile, because we have one piece of ground truth. So yeah, tons of stuff with Huygens. And just the fact that you've got the little pebbles. I mean, this is our close-up view of the surface. So all of that is just solely from Huygens.
I have a comment here. You mentioned about the recorder, and it's a half giga.
Yeah, the half gigabyte recorder.
Okay, I worked on all the spacecrafts, but one of the Magellan spacecraft. Do you know how large the memory was?
I don't. Do you know?
We had, yeah, of course I know.
See, that's what I love about the von Kármán lecture series.
Yeah, we had only 32K.
Wow, 32K. So you can imagine when I got to there.
More than that. We had to design, and actually I was the one who did that, saving mechanism for the mission, which was exercised several times.
Yes.
Do you know how much memory we had for that?
I don't think I even want to imagine.
1K.
1K. It's
We had
terrifying.
the whole attitude control in 1K. And I left some spare for input-output.
Technology has really changed. The difference between, say, the Voyager spacecraft and... Oh, sorry.
Yeah, I know. I mean, of course, I mean,
It's...
the question here is about the Voyager, too. You mentioned Voyager. That's a question.
I don't remember the amounts on Voyager anymore. I used to have that data in my head, but that's one of the great things about working at JPL and also working for NASA. It's sort of this, as technology marches on, you get this more and more capability in your spacecraft, and things that we couldn't even dream about 20 years ago now are routine. It's exciting.
Another small piece of information.
Okay.
With the Voyager, with the Magellan, which used to be called Venus Radar Mapper. Before the manager, the system manager was Gary Parker. Many people probably would know. He told me we cannot lose the spacecraft. The Russians lost 2 Venera spacecraft because they got disoriented.
By the way, all managers say that. Just so you know. There's no manager at JPL who would say that.
But the Russians lost 2 spacecraft, 2 Veneras before we did. I said, you will be fired if you lose the spacecraft.
Yeah, I've heard that one too. You'll be fired if you.
Yeah, well, I retired.
Yeah.
I did not.
So actually, Tessa, if you had another question, you could. So let me look at this one. Is there any evidence of tectonic activity on Titan? This is from one of our Ustream watchers. And the answer is yes. We have those pictures of the mountains that I showed. Let me See if I can zoom back there pretty quick because I don't remember there you go. This is, here's your evidence of tectonic activity on Titan, is in the long, whenever you have long, straight features. Yeah, Tessa.
Okay, this is actually going to be my last question because
Okay.
the other questions people asked kind of answered
Excellent.
the other ones I had. When you said that the winds go from west to east,
Okay,
okay, now I'm always fascinated by orientation
okay.
with space, okay, because, we're not talking Earth. So when you say west to east, this is going to be relative just to the rotation that
Yeah, so let me show
Saturn
you,
does.
let me go back to one of my nice pictures, big picture of Titan. Okay, so when we say when we measure, remember Titan is tidally locked, so 0 degrees longitude is facing Saturn.
Yeah.
And so what we have is we have a coordinate system that is just north, east, southwest, but we go 0 to 360. And this is moving, so when we say west to east, we mean from this here, this direction this way, okay? Some people put, some people do plus or minus 180 degrees and it just confuses the rest of us. I wish they'd stop.
Right.
So when we say west to east, now here's a tricky thing. So do the winds move west to east? Well, not exactly. All the dunes are showing that the wind pattern that created the dunes are west to east. But every single global circulation model that anyone has done for Titan has the atmosphere moving east to west. And yet the dunes clearly show west to east. And so this has been a bit of a mystery. I think I saw a paper go by in the last year or so that it said what we think might be happening is that in these short, intense southern summers that you get peak winds that go west to east, and that what's happening is that the sand or the hydrocarbons on Titan, the coffee grounds, only respond to the peak winds. And so they're only responding to those west to east bursts, but the general winds travel east to west on Titan. So you have to be careful with that one. I tried to sidestep that thinking maybe no one would ask, but you asked.
Thank you.
You're welcome. Let me see, there's another question here. What are the next steps? What is coming up and about studying Titan in future years? Well, we've got still many years left of the Cassini spacecraft, hopefully out to 2017 if we're funded to do that work. We have perhaps a competed mission like the Titan Mare Explorer might get chosen by NASA to go to Titan. I'm sure in the next round of Discovery and New Frontiers, Discovery, that there will be another mission to Titan. And I would very much like to see NASA just flat out say, we need to have a directed mission to Titan. It needs to be big, it needs to be flagship, and JPL, you guys are awesome at this, go off and do it. Because look at Cassini, that's what they did with Cassini, right? Voyager flew by and it's like, oh my gosh, this place is way too interesting, we have to go back. So NASA headquarters said, go, we direct you, JPL, to do something that's really hard, and we are convinced that you will do it really well, and we're going to give you the money to do it. And Cassini came in on budget. We did not run over. In fact, when we launched the spacecraft, we gave millions, I think tens of millions of dollars back to NASA because we did such a good job with the money. So outer planet flagships, man, we know how to stay in budget. Like the Mars, it's a friendly rivalry, but directed flagship missions, outer planets, knows where it's at. Next question.
So my question is about the landing side of Huygens. In the image taken from the sky, you could see right, and you could see the shoreline kind of thing, right? But if I pick up a random location on the Earth, it could be in the ocean, it could be in the huge continent, but the chance that you land near shoreline is extremely low. So I'm just wondering if, the fact that you landed near the shoreline is just by chance or
Pure
you
luck.
aimed it. It's
Absolute pure luck. We didn't know what the surface of Titan looked like at all. We didn't have any reason to pick any particular location, so we let the navigators pick it. Where's the easiest spot to land? We'll land there. Yeah.
So what was the chance? 1 in million or kind of thing?
Well, so here's all the different, lines. There's the, these are shore-ish lines. There's a lot of interest. I think no matter where Huygens would have landed on Titan, it would have been ridiculously interesting. But I'm probably a little biased.
Thanks.
Sure. And we have another question. Yeah, just come up here and stand in a line. That's fine.
Yeah, just curious on that one photograph where you said it's the alien landing strip.
Yeah, it's just funny.
What is that?
It's one of these, sorry, I need to go to the Huygens stuff. There's my little animation that I'm in love with. There it is. It's just one of these channels right here. If you were to cut this one off right there, it would look straight. That's all. It's just a river channel.
I'm disappointed.
Yeah. And it's also funny for me to say the alien landing strip. It's a good joke. I like it. Yeah.
Thank you.
Sure.
I think this is an appropriate question to follow up with that. You'd prefer somebody asking about the possibility of life on Titan, so I'm gonna ask it.
Titan is very interesting astrobiologically, right? There's a lot of interesting chemistry. It's the kind of chemistry that here on the Earth, when you put hydrocarbons in a glass bottle with liquid water and you zap it with electricity, you get amino acids and all kinds of interesting stuff. And it is just sitting there out at Titan. Of course, it is bitterly cold, bitterly, bitterly cold. But an interesting thing happened on the way to Saturn. One of the leading astrobiologists in the world, Chris McKay, said that given the instrumentation on Cassini, if there was methanogenic life, Cassini would see the following three things. There'd be something going on, that there would be none of this ethane that we've all expecting these oceans of ethane. There would be a depletion of acetylene on the surface, and there would be also a surface hydrogen sink. If the little creatures were sitting on the surface, they would eat the hydrogen, and you would have a sort of a sink in the hydrogen. So we get there, and what happens? We've got no global oceans. Ralph Lorenz goes off and does a whole Titan inventory, and there's a lot less ethane and methane than we thought. Check. After years of doing his studies, Roger Clark, who works on the visual and infrared mapping spectrometer, map everything, and one of his findings, there's sort of a depletion of acetylene. We don't see as much as we should. Where is it? And then Darrell Strobel comes along a few years later and does a giant sort of global circulation model thing. And there's a lot of knobs that you can fuss with in a global circulation model, and he fussed with the one that says deplete hydrogen at the surface, and the thing converges, right? Boom, boom, boom. So of course, front page of the newspaper, alien life found on Titan. What we're saying is it's now more interesting to talk about it, isn't it? But there are other explanations for all of those things, right? And so you now that you're at the point, so for example, Darrell could have fiddled with his knobs differently, and maybe he would have gotten his model to converge. Maybe there's a different way to get that atmospheric model to work, and it doesn't have a depletion of hydrogen at the surface at all. But maybe that's real. So so now like the focus of the modeling world, let's make sure that's right, because it's an important one, and it's one that kind of is the most, I don't want to say the weakest. It's the piece of data, because it's not exactly data. It's a model explaining data, right? So it's the weakest piece of the three that we have in terms of data. But every day that Roger looks at Titan, he's got his grain size stuff down. He's got his atmospheric models are getting better and better all the time. So that lack of acetylene, that's looking more and more solid as time goes on, and this the ethane depletion, that's looking real. So now we have to start thinking: are there other explanations that would cause those three things? And there are. There are like mechanical surface things that would cause that. But those are kind of hard to, you kind of have to have just the right thing working out, right? And we don't like explanations where you have to have just the right thing working out. So, but there's a lot of attention on it now. And so it's not crazy talk to be talking about what can we learn from Cassini and what does it tell us about a life that might exist on such an alien world. In fact, another kind of nice mental exercise is to think about the universe in general. The universe in general is populated with M-type stars, and probably around M-type stars you're going to have things that look a lot more like Titan than the Earth. And so maybe Titan is the model of the most common planet in the universe, not Earth, Titan. And then this conversation becomes even more interesting. So it's interesting work that's being done, and take a look at it. Chris McKay's paper, he brilliantly put it out just before we got to Saturn, which is what good scientists ought to do. You predict before you have data, so that your predictions, see, I'm predicting in the absence of data, that way it means something. So good stuff.
Sounds like a good selling point for the mission you guys are trying to do.
Well, you know, Titan really just sells itself. I mean, how could we not go back, right? I mean, look at this. It's unbelievable. We have to go back. And with that, I don't see anyone else lining up. I'm happy to stay for questions, but thanks so much, everybody. I hope you enjoyed the lecture.